Okay, let's talk a little bit about the common ion effect. And it's a consequence of Le Chatelier's principle. That is, if I've got this calcium fluoride and I add fluoride, say from sodium fluoride, where the sodium's not going to affect the equilibrium at all, just some spectator ion, the equilibrium is going to shift away from the increase, which is the fluoride ion. And so it'll shift towards the formation of more solid calcium fluoride. So adding a common ion that's on the product side, as it is in one of these salts, will produce a decrease in the solubility of the calcium fluoride compared to what is normal. If you look at that as we add sodium fluoride, we can see the solubility in pure water up there at the top. But then as I add fluoride and increase its concentration, that molar solubility drops quite dramatically. And that's the effect of a common ion if there's excess of one of the ions present in the insoluble or sparingly soluble salt. Now, if the fluoride's removed, then the equilibrium would shift the other way. Fluoride can be removed by adding a strong acid. And so if I add H+, remember HF is a weak acid, so some of that fluoride will get bound up by the acid and therefore is inaccessible by the competing equilibrium for the calcium fluoride, and therefore the solubility will increase. So as pH decreases, the solubility increases, and its effect can be quite dramatic. We can see the molar solubility of the calcium fluoride, and as I approach a pH of 1, the solubility actually becomes quite significant, where it's not very soluble at the beginning. So let's mark these true or false. And so here's some statements about the common ion effect. Silver chloride can be made more soluble with the addition of ammonia. Yes, we're going to talk about that here in a second. Anything that'll tie up one of the ions, it turns out ammonia will bond with the silver to keep it out of the silver chloride equilibrium. Ammonia can bind to certain metals and cause that effect to happen. Calcium fluoride can be made more soluble with the addition of hydrochloric acid. We just talked about that. Lower pH is going to bind up the fluoride ion and therefore make it more soluble. Lead iodide can be made more soluble with the addition of sodium iodide. Now, iodide's a common ion to the equilibrium. It's going to make it less soluble, not more. So that one's false. And so talking about the ammonia idea, let's revisit that. So if we add ammonia to silver chloride, white precipitate, but if we add ammonia, we can get that precipitate to start to redissolve depending on how much ammonia we add. And it turns out the ammonia forms a complex with the silver, drastically increasing its solubility. And any types of things like that that combine the metals that are soluble and forms a soluble complex can do very much a similar thing. We'll focus on ammonia for the purposes of this class. And again, a consequence of Le Chatelier's principle, because it's the equivalent of removing the silver from the solution. So that should explain that true false you saw before. Let's consider barium sulfate. Now, and I've given you a Q and not a KSP. You can do Qs for KSPs as well, just like you can any other equilibrium. So if Q is bigger than KSP, then precipitation will continue to occur. That is, I've got too many ions, therefore I'm going to have to precipitate some until Q equals KSP. If Q equals KSP at equilibrium exists, essentially what I've got is a saturated solution. If Q is less than the KSP, I could dissolve more. I could continue dissolving, in our case, barium sulfate, until they're equal, at which point I would have a saturated solution again. Based on KSP, we can also selectively remove ions from solutions. Say if we got zinc versus copper. If I add sulfide, say in the form of ammonium sulfide or sodium sulfide or something like that, both of those salts are insoluble, but the copper sulfide, copper 2 sulfide, is 6 times 10 to the negative 37th, but that's less soluble than zinc sulfide, which has a KSP of 2 times 10 to the negative 25th. Therefore, the cupric sulfide will preferentially precipitate. And you can tell because the salts are actually different colors. The cupric sulfide is black and will precipitate out, and any of that blue to blue-green color of copper 2 ions in solution will disappear, and you'll get a black precipitate, indicating the copper is what precipitated, leaving a color solution of zinc ions. If I add some more sulfide, then you'd get a white precipitated zinc sulfide. So you can tell which one's precipitating by the colors of the solutions and the precipitates. Ions can be separated from one another based on their solubilities. Again, sometimes you can just one soluble and the other one's not. For example, if I add HCl to a solution containing silver and copper ions, the silver precipitates because the KSP for silver chloride is 1.8 times 10 to the negative 10th, while the cupric ion remains in solution because cupric chloride is water soluble. So removal of one ion but not the other, we call that selective precipitation, and we can use the solubilities to actually do that. Where choose something where one of the ions is soluble and the other one isn't, or choose one where one salt is significantly less soluble, so it'll preferentially precipitate out. So let's look and see if a precipitation would form in this case. If I mix 0.15 moles of sodium chloride with 0.15 moles of lead nitrate to form 1 liter of total solution, we know that lead chloride is insoluble, but how much can we dissolve? It's based on that KSP, and we worked one with lead chloride in the previous video. So what we have to do is compare the Q to the KSP. And so if we go to do that, we've got a reaction, our KSP. So our Q here then is going to be equal to the concentration of the lead ion, concentration of the chloride ion squared. So look at the exact same type of formula, except these are not saturated conditions. What you plug into a KSP is for a saturated solution. These moles over here may generate a concentration bigger or smaller than the saturated amount. That's what we have to figure out. So if I go and plug and chug, if we get 1 liter solution, this means this is 0.15 molar. And this is 0.15 molar quantity squared. So then let's figure out what the Q is. And so that's going to essentially be 0.15 cubed. And so we get 3.375 times 10 to the negative third, which we'll round that to 3.4 times 10 to the negative third for sig fig purposes. Now, is that going to be bigger or smaller? It's a smaller negative exponent, so that means in our case Q is bigger than the KSP. So that means in this case I've got too many product ions, so if Q is bigger than KSP, that means I get precipitation. And so we will get precipitation of lead chloride until these two are equal. So the excess will come out of solution.